Hello. So we're going to go over all of the it's titled Eigen-everything. So eigenvectors, eigenvalues, even eigenbases for linear transformations. That comes up once down here. But before we get going, we're going to need to know some general properties of eigenvalues and eigenvectors that will help us along the way. So geometrically, what is an eigenvalue and an eigenvector? So when we apply a linear transformation, let's say this is a random vector in R2, let's say we apply an arbitrary linear transformation, most of the time, if we plot out the span of that original vector, most of the time that vector will get kicked off of its own span, and it will no longer be parallel to that span. But some of the time, if you choose a very special vector, it will only be scaled by a certain amount. It will stay exactly on its span. And this vector, this span here, is an eigenvector, and the amount that this original vector gets scaled by is the eigenvalue. So with that in mind, that'll come up later, not necessarily for this first one, but we'll need to know that in a bit. Okay, so let's find the multiple eigenvalues of A. So we pretty much need to solve for all of our eigenvalues. If we plug in A minus lambda I into here, we can find our determinant and set that equal to 0. We can pull out 2 minus lambda because it's in a row by itself, and negative 1 minus lambda because it's in a row by itself, and multiply it by the determinant of that matrix right there. So that's 2 minus lambda multiplied by negative 1 minus lambda multiplied by the determinant of this matrix, which is negative 2 minus lambda times 5 minus lambda plus 6 is equal to 0. So in here we can rewrite this as, let's see, lambda squared minus 3 lambda minus 10 plus 6 is minus 4, and we can factor this to lambda minus 4 lambda plus 1. So we can reconnect this with our 2 minus lambda and our negative 1 minus lambda. And where do we have a multiple eigenvalue? If we set this equal to 0, well, we see that lambda is equal to 2. Lambda is equal to negative 1. Lambda is equal to 4, and lambda is equal to negative 1. So negative 1 is our multiple eigenvalue. It has a multiplicity of 2 here. We have 22. We're finding the eigenvalues. So yet again, because this one position is in a column by itself, we can plug in negative lambda along that main diagonal and multiply 1 minus lambda by the determinant of this matrix right here. So 1 minus lambda multiplied by that determinant, that will be 2 minus lambda multiplied by 8 minus lambda plus 5 is equal to 0. This is 1 minus lambda multiplied by lambda squared minus 10 lambda plus 16 plus 5 is what? Plus 21. So 1 minus lambda multiplied by lambda minus 7, lambda minus 3. So our eigenvalues are 1, 3, and 7. Oh, sorry, I should be clear. We're setting this equal to 0. Whatever. Okay, here's where our properties start to come in handy. So you could go and directly solve for all the eigenvalues and eigenvectors, and then match up this guy to see what eigenvalue it corresponds with. But because we know that if this is an eigenvector, then when we apply the transformation to this as our starting point, values will only be scaled. So this will only be multiplied by a certain amount. It will not be it will be a multiple of itself. So essentially what we can do is set up 0, negative 2, 2, 0 and multiply it by negative I1, we will get another 2 by 1 matrix with entries 2 and 2i. So what do we need to multiply each of these entries to get to our output vector? Well, we need to multiply them by 2i. So the eigenvalue associated with this eigenvector is 2i. So that's our answer, and it's as easy as that. Okay, 14, let's find the sum of all the eigenvalues of A. Okay, so the sum of the eigenvalues of a matrix is equal to the trace of that matrix, which is the sum of the main diagonal entries. So our answer is 9. That's it. 14, so we're dealing here with an eigenbasis. So what they're asking is, we have a transformation from R2 to R2, and which of the following is a basis B for that transformation with the property that the beta matrix for T is a diagonal matrix. So I still am not completely sure what a beta matrix is. All I do know is that when they ask us for this, what they're really saying is find the basis in which applying the transformation is the same thing as just scaling a vector by a certain value, and we know that occurs when we're dealing with eigenvectors. So if we have some transformation, let's say we have two eigenvectors there. If we're able to transform into from the normal basis, so with our normal 1, 0, 0, 1 basis vectors, to the basis represented by our what are they called? The eigenvectors. Then all we'll have to do for any input vector is just scale them along these eigenvectors. And so that will allow our whatever beta matrix to be diagonal. So in the end, really, we're just finding the eigenvectors of A because they satisfy this property. So we're solving 2 minus lambda multiplied by 3 minus lambda minus 6 is equal to 0. Lambda squared minus 5 lambda is equal to 0. Lambda is equal to 0 and 5. So for lambda is equal to 5, a minus lambda I will become negative 3, negative 6, negative 1, negative 3, simplifying down to 1, 3, 0, 0, and so we get an eigenvector of negative 3, 1. And did I screw that? I think I already screwed that up somehow. Should we not have gotten 3, 1? Because I'm not seeing that in any of the answer choices. What did I do? What went wrong here? 2, negative 1, negative 5, so that becomes negative 3. Oh, this becomes negative 2. I can't count. Yeah, so we'll get 1, 2 there, and so we'll get negative 2, 1. Okay, and then for lambda is equal to 0, our other eigenvalue, we get 2, negative 6, negative 1, 3 for a minus lambda I, which simplifies down to 1, negative 3, 0, 0, and so we get 3, 1 as an eigenvector. So in the end, the basis for which our transformation matrix is diagonal will just be composed of these two eigenvectors there. 19, same thing that we were doing earlier. We can just multiply this matrix for the transformation by this vector, and assuming it's along an eigenvector, it will be scaled by a certain value, and that value will be the eigenvalue associated with that eigenvector. So 0, negative 4, 0 multiplied by negative I, 1 will give us 4 and 4i. So the value we need to multiply 1 by to get 4i is exactly that, 4i, so there's our answer. And finally, suppose that 2, 1, 3 is an eigenvector of that matrix right there. What is A? So we can do the same thing. If we take that matrix there, 2, 1, 1, 1, 2, 0, A, 5, 1, and we multiply it by this input vector 2, 1, 3, we know that the 3 by 1 matrix that we get out should be just a multiple of the input that we put in, and we'll be able to see what that constant multiple is, that eigenvalue, from the first two entries, and then the third one we should be able to adjust A to fit the pattern we've already seen. So 4 plus 4 gives us 8, so given that this is an eigenvector, we know that lambda is equal to 4. Then for our second entry, we get 2 plus 2 plus 0, which is 4. That still checks out. So we want to get 12 for this bottom element here, and we see that this is 2a plus 8, and therefore a is equal to 2. And that's really it. It's just when it comes down to computing eigenvalues and eigenvectors, it's just solving the determinant of a minus lambda I equal to 0. Sometimes you have to bring in some properties of determinants to compute some of the bigger ones. But in the end, just knowing that and knowing the graphical properties of eigenvalues and eigenvectors will get you a long way.